Hey there, focused learners, and welcome to today's Explainer. Today, we're getting into something that's honestly just fundamental to both engineering and physics. We're talking about how machines react to change over time. We're drawing directly from an awesome chapter by Dr. Roshakim Muhammad Isa to explore this idea of time response. Because, whether you're dealing with a simple little electrical circuit or some massive heavy-duty industrial machine, you absolutely have to understand this concept. It's literally the language of how systems behave.
Think about it like this. When you're driving and you suddenly just stomp on the gas pedal, does your car instantly teleport to 60 miles per hour? Well, no, of course not. There's a whole process, right? The engine revs up, the gears shift, momentum builds, and the car accelerates over a period of time until it finally settles into that cruising speed. And control systems engineering? It looks incredibly closely at that exact gap, that fascinating journey between your initial action and the final reaction.
So, to make sense of all this, here's our roadmap for today. First, we're going to define the journey to steady state. Then, we'll explore first-order systems, followed by the magic time constant. After that, we'll get into the bouncy complexity of second-order systems. And finally, we'll wrap up by looking at how engineers actually design the perfect response. All right, let's dive right into Section 1, Journey to Steady State. So every control system's time response is actually split into two really distinct parts, the transient response and the steady state response. You can kind of think of it as a duality. The transient response, that's the messy, active journey. It's how the system behaves right after an input is applied, as it travels from its initial state toward its final state. It's where all the unpredictable action happens. The steady state response, on the other hand, is the final destination. It's how the system acts as time approaches infinity, long after all that initial chaos and bouncing around has completely faded away. To truly understand a system, we have to understand both the trip and the arrival. Which brings us to Section 2, the first-order system. This is the absolute simplest type of journey a system can take. Now, in the world of control systems, this simple block diagram loop perfectly represents a first-order system. We're talking about systems that really don't have complex, bouncy behaviors. Think of basic setups like a simple RC electrical circuit where a capacitor is charging up, or a thermal system like a cold room gradually heating up when you turn on a radiator. It's straightforward. The input goes in, the system processes it through a simple transfer function, and bam, we get an output. But to really figure out what a system can do, we have to test it with different types of signals. Now, what's really interesting here is how we simulate real-world actions using math. Our very first test signal is what's called the unit step input. Mathematically speaking, using Laplace transforms, it's represented as 1 over s. But practically, what does that mean? Well, it's the exact equivalent of suddenly flipping a light switch or instantly pushing a throttle to a specific position and just holding it there. It jumps from 0 to 1 instantly, providing this sudden, constant demand on our system. Next up, we have the unit ramp input, which is represented mathematically as 1 over s squared. If the step input was flipping a switch, the ramp input is a lot more like turning a volume dial up at a perfectly steady, constant rate. The signal just increases linearly over time. And mathematically, this ramp function is actually the integral of the step function. Basically, we are asking the system to chase a target that is constantly moving away from it. So when we feed that ramp input into our first-order system, you'll see a thin, straight line. That's our input target constantly moving away. And that thicker, curved line, that's our system's actual output, trying desperately to catch up. But notice the visual gap between the two lines, the one that persists even as the lines completely straighten out. As time approaches infinity, that gap is still there. We call that the steady-state error. The system is definitely following the ramp, but it's always just a little bit behind. Okay, our third and final basic test signal is the unit impulse input. Mathematically, it's literally just the number 1. In the physical world, though, it's a sudden, extreme shock to the system that lasts for practically 0 time. Think of it like hitting a bell with a hammer, or a massive sudden spike in voltage. It's actually the mathematical derivative of that unit step input we talked about earlier. If you followed the curve downward here, you can see exactly how a first-order system reacts to that massive hammer strike. The system gets this huge shock right at time 0, which instantly spikes the output. But because the input disappears just as fast as it arrived, the system spends the rest of its time just recovering. It bleeds off all that energy, and the curve exponentially decays over time until it eventually just settles all the way back down to 0. So, we know these systems transition from state to state, but what actually determines how fast they do it? Let's get into Section 3, the magic time constant. There is a really fascinating property of first-order systems right here. When you look at the curve of a system responding to a step input, you'll find the time constant, which we denote with the Greek letter tau. And tau isn't just some random arbitrary number. It is the exact, specific amount of time it takes for the system's output to reach precisely 63.2% of its final steady-state value. Literally, no matter what a first-order system is made of, at time equals 1 tau, it will always be 63.2% of the way through its journey. Let's translate that math into some real physical intuition. You can essentially think of tau as the system's speed indicator. A large time constant, a high tau, means the system feels heavy, it's sluggish, it takes a really long time to get going and finally reach its target. On the flip side, a small time constant, a low tau, means the system feels incredibly tight and snappy. It's super responsive, rocketing toward its final steady-state destination in an absolute flash. And this brilliantly illustrates that exact concept playing out. We're looking at two exponential response curves. The red curve has a time constant of 50, and the blue curve has a time constant of 100. Because the red curve has the smaller time constant, it climbs much steeper. It easily wins the race to the steady-state destination of 1. Meanwhile, that sluggish blue curve takes nearly twice as long just to catch up. All right, prepare yourselves for a bit of a jump in complexity. Let's move on to section 4, second-order system bounces. Because in the real world, things definitely don't always smoothly slide right into their final destination. Sometimes they bounce. To really ground this, the source material gives us a fantastic physical example, a forging hammer dynamic system. Unlike a simple little heating coil, this system has 3 fundamental ingredients all interacting together. It's got mass, represented by M, spring stiffness, represented by K, and a damping coefficient, represented by Kd. The very second you introduce a mass and a spring together with a damper, you fundamentally change how the system travels through time. Energy gets stored and then it gets released, and that causes oscillation. Looking at the step response here, we basically ask the system to jump up to a specific target value, that dotted line. But because of the mass and the spring, it doesn't just smoothly slide up and stop. No, it rockets right past it, overshoots the target, gets pulled back by the spring, completely overcorrects, and then bounces up and down in this decaying wave before finally settling down at the steady state. In control systems, we call this an underdamped oscillation. So the absolutely crucial point here is, how on earth do we control that bounce? Well, we use a mathematical property called the damping ratio, represented by the symbol zeta. It mathematically dictates whether the system oscillates wildly or just glides to a nice, easy halt. If your damping ratio is less than 1, the system is underdamped. It's going to overshoot and be bouncy. But if you perfectly tune it so the damping ratio is exactly 1, the system becomes critically damped. That means it'll return to its equilibrium completely smoothly, without a single bounce. Connecting the math back to what we see, case 2 here perfectly highlights what happens when the damping ratio is greater than 0 but less than 1. This creates that very specific, classic underdamped curve. You get this incredibly rapid initial rise, a very noticeable overshoot, and then that decaying, bouncy amplitude that slowly gets squeezed out by the damper, until the whole system flatlines at the target steady-state value. Which brings us to our 5th and final section, designing the perfect response. Now, we've seen how these systems behave, but how do engineers actually use these bouncy curves in the real world? Well, when evaluating that messy, transient journey we just looked at, engineers definitely don't just eyeball it. They use incredibly strict chronological specifications to grade the system's performance as it unfolds over time. First, they measure the delay time. Then they measure the rise time, and finally, they measure the peak time. Mapping all of these out chronologically gives us a highly detailed, super accurate blueprint of both the system's speed and its stability. So let's briefly define what these specs are actually measuring. Delay time is simply the time it takes for the response to reach exactly half of its final destination value for the very first time. Rise time is how long it takes to reach that final value for the first time, right before it overshoots. By strictly measuring these, engineers can actually set allowable tolerances for the final steady state. They're essentially drawing boundary lines, like say a 2% or 5% error margin, which ensures the system is actually reliable and safe for real-world application. Because, absolutely nobody wants to drive a car with a 50% bounce margin. And that brings us to the end of our journey today. We've seen how time constants dictate speed and exactly how damping ratios control the bounce. At the end of the day, it all comes down to manipulating those variables. So I want to leave you with a question to ponder. By carefully tuning the mass, the spring, and the damper, what kind of journey are you going to engineer for your next system? Is it going to be a sluggish crawl, a wildly bouncy ride, or a perfectly smooth glide straight to the finish line? Thanks so much for joining me on The Explainer. Keep learning, and I'll catch you on the next one.